Thank you. Okay, well, thank you very much. I'm going to be talking about something which is probably not on the horizon in the short term, but is going to be a long-term trend. I predict that within 10 to a dozen years, this will start to become a noticeable bit of technology. And what I'm going to be talking about is something that I like to refer to as the last frontier, and of course that's a little bit of a joke. There is never a last frontier, but this is arguably an important frontier that we can all look forward to filling very soon. So let's just start with take a quick look at the electromagnetic spectrum. We notice that there's use for everything from DC to daylight, except, interestingly enough, this middle range of frequencies that's centered roughly around 1 terahertz. So roughly from 300 gigahertz to 3 terahertz, there does not appear to be a whole lot of activity. And there's a very interesting reason for that. And of course, it's hard to believe that there aren't uses for it, since that would make it sort of a unique part of the electromagnetic spectrum if that were true. So let's see if we can understand a little bit more about what's going on. If you look through the literature, you discover that there has been quite a bit of quiet research done on terahertz electronics for 40 years, actually. And the reason you haven't heard of it is it has not yet become commercially significant. So it kind of gets buried in the back pages of specialized journals. But already people have identified the possibility of using terahertz waves to image through opaque objects like clothing, which clearly has some interesting implications for security applications. But you can also use it for medical applications as well. It has the ability to penetrate through bodily tissues to the depth of about 1 millimeter or so, depending on the tissue, which means you can do things like this. You can detect cavities forming in your teeth while you can still do something about it. Today, we have the ability to image through teeth, but only using X-rays. And X-rays are ionizing radiation, which kills cells and can cause cancer. So you clearly don't want to routinely X-ray teeth just to solve this problem. But terahertz waves have a photon energy that's well below the bond strengths of any biological tissues. So you don't have to worry about this problem of tissue damage. Other applications include spectroscopy. It turns out that many molecules of medical, environmental, and security interest have resonances in the terahertz band of frequency. So you could imagine lighting up a sample with some chirp of terahertz energy and look at the return signal, and you can infer something about the chemical composition of the material you've just illuminated. So that's another very exciting thing, that you'd be able to look at some substance and very quickly determine whether it was dangerous or benign. Again, this is something you often want to know right away, not a week later after a lab has had a chance to do its normal analysis on it. And the application that I'm going to focus primarily on today is this one, if I can get the clicker to behave, is what I'm calling extreme wideband communications. As you all notice, we live in a digital age, and it seems that the human thirst for data rate can never be quenched. We always want higher data rates. No matter what data rate we are given, we complain that it's not enough. And so if we, it's future. So we'll be focusing quite a bit on technologies that might support a future in which XWB communications becomes mainstream. If we take a look at these applications in a little bit more detail, again, the imaging applications range from medical and dental and detecting concealed threats, but also include manufacturing process control. There are lots of things that you'd like to be able to detect before it gets to the consumer's hands. And right now there's no simple way of doing things like imaging through certain kinds of materials that might be damaged by X-rays. Again, terahertz waves are excellent for that. For communications, not only can you get very, very high data rates, but it turns out that since terahertz does not travel very well through atmosphere, you automatically are guaranteed very high spectral reuse. So I can carry on a conversation here at terabits per second, and the person maybe 10 meters away will not be bothered by my conversation going on over here. So if we use as one measure of network capacity the total number of bits per second per square kilometer area that we can serve, terahertz frequency bands are extremely attractive for that. So we can serve a large number of people at extremely high data rates. Okay, if we can get the... I think you need to wiggle the mouse every once in a while just to keep it from going into power down. So sorry, you'll get some exercise with your fingers. Now, if we take a look at how the technologies currently in use might scale toward the terahertz band of frequencies, we find that there are some great technological difficulties. For engineers, that's a good bit of news. We always want to have problems to work on, and the more significant the problems, the more they'll pay us, so that's a good thing. So let's take a look at how scaling trends affect our ability to deliver some terahertz electronics in the future. Right now, the way that we get high speed is we shrink transistor lengths. That's not a big bit of news to you, I'm sure. But let's take a look at what the implications are of that shrinkage for terahertz applications. What happens is that we have to trade off device breakdown voltage in exchange for the high speed. If you work through the math, and don't worry about the equations if you're just willing to trust me on this, the output power that we can get out of a device just from this scaling behavior implies a diminution in output power per device by this quadratic factor. It goes down as Ft squared. So if I double Ft, I reduce by a factor of 4 the amount of power I can pull out of that transistor. That's pretty bad. So we get high-speed devices, but we can't get much power out of them. The news is actually even worse than that. This is not the only scaling property that we have to fight. The other scaling property is this. If you consider a single transistor, it has to be driven by something else. And that something else will not want to work into a short circuit. So we can't just leave the device input impedance unconstrained. When we scale the device, we have to scale it smartly so that the input impedance stays within some reasonable practical range. In this case, what we'll argue is that a practical range is that the capacitance has to be scaled downward so that the input impedance is constant. And if you work through all that mathematics, what that implies is that as you go up in frequency, you need to shrink the width. Well, shrinking the width reduces the current, and power goes as the square of current. So once again, we find that the power output from the device goes down perhaps as much as another quadratic factor. So we have two quadratic factors, one from voltage breakdown considerations, and another one just simply from having to keep the input impedance from going too low. And that in turn implies a reduction in width, which reduces the current. So unfortunately, as we go faster, the output power from the devices drops as perhaps the fourth power of frequency. Now, what you do when you work these kinds of equations is you say, well, these are very simplified equations. There's probably a lot that I've missed, and maybe the reality is better than that. So then what you do, in my case, because I'm lazy, is you force your graduate students to go through the literature and assemble data from all the publications that they can find within a short time to see whether or not these scaling laws are correct. And unfortunately, what we find out is that they are. If you take a look at all these data points and just sort of do a rough fit, you find that they do conform to a 1 over f to the 4th curve. That's very, very bad news. And then you might say, well, but wait a minute, that's semiconductors. We expect semiconductors to have a problem as you go higher in frequency. So maybe the solution lies in the photonics world. So maybe we should just fire all the double E's in the future and make them all learn photonics. But then you find out photonics also has its own scaling problems, and that's not a solution either. Photonics doesn't look very good until you get up to sort of tens of terahertz or 100 terahertz. So there's this funny region closely centered around 1 terahertz where neither semiconductors nor photonics works well. That's very bad news. So here we have a lot of applications just waiting to be served, but we have no devices to serve them. And the scaling trends that I just described are actually fairly universal. They apply to pretty much any semiconductor technology you can imagine, whether they're compound semiconductors or silicon. They will all suffer the same basic shape. The choice of material only translates these curves up or down, but it does not fundamentally change the slope. So what this curve says is if I want to go up a factor of 2 in frequency, my output power will drop by something like a factor of 16, more than an order of magnitude, just to double the frequency. So that's a serious problem. And you might say, well, why is that a serious problem? If my power is this low, okay, that just means I go short distances, but maybe these applications are going to be short distances. Well, let's calibrate ourselves on what short might mean. To To figure that out, we need to get some data on atmospheric absorption in the terahertz band of frequencies. Here's a collection of curves showing absorption in dBs per kilometer on the vertical axis as a function of frequency. Yeah, I've got to keep wiggling that mouse. Oops, so I got to go back here. So if we take a look at this set of frequencies here, you notice that there are some reasonable attenuation minima at hundreds of gigahertz, close to a terahertz, and then rising kind of in some gradual fashion on average with some fine structure here corresponding to molecular resonances of things like nitrogen, oxygen, and water. If we take a look at what this curve implies, though, you notice these are all locations with the letter B. The guy who constructed these curves just had a thing for the letter B. Don't ask me why. But if we look at these curves, we see that there's a huge variation depending on the local climate. In this case, you have Buffalo, New York, during the winter, which is fairly dry, so you don't have much absorption at all. And over here we have Bangkok, which is terminally humid, and we find that water just loves to absorb terahertz, and you don't get much distance. So we do have to worry about not only the fact that you get high attenuation at terahertz frequencies, but also that that attenuation is quite variable as a function of local conditions. If we take that data and present it in a slightly different way, if instead what we want to do is present the information in a form that communications engineers might find more useful, we discover that it might be useful. Oh boy, we've already reset this. Okay, let's. Hello. Okay, so if we take a look at this, this is now plotting that same information in this different form. What we're now looking at is the 10 dB attenuation range in meters as a function of frequency. So if I'm interested in how far I can go before suffering a factor of 10 reduction in power, this is what this curve is telling us, with some of that local climate information kind of absorbed into three coarse categories: humid, dusty, and clear. And what we find is that at 100 gigahertz, you might be able to expect kilometer scale distances, which is still pretty good. If we get to the terahertz band, we find we have to be very careful about what we choose, but we can still imagine getting 10 dB attenuations at hundreds of meters under favorable conditions. So tell me how much attenuation you think you can suffer before your link margins degrade to unusable values, and we can use this plot to sort of guess what the typical communications range will be. Now, this curve tells us something important about what the technologies will have to support. They will have to support substantial transmit powers if we want any kind of reasonable range. And what we mean by reasonable range in this case apparently is denominated sort of in 100-meter sorts of length. So if I want to go a kilometer, I'm going to have to suffer perhaps 30, 40, 50, 60 dB attenuations, which means I'm going to have enough transmit power to still provide enough receive energy for my receivers to work. And if you think about that receiver part, it's going to be built out of the same transistors. I'm pushing the edge of technology. They're going to be a little bit noisy. They're not going to have much gain. It's going to be difficult to have link margins sufficient to keep this thing working. So these are all sort of in service of the argument that we need technologies that can simply provide large amounts of transmit power. Otherwise, we can't really make these communications links work over reasonable distances that we are accustomed to using. Now, what are some of the supportive technologies? Well, because of the extreme frequencies, you'll find that the architectures are very unsophisticated. If you take a look at the block diagram for a cell phone, it's much more interesting looking than what they are for terahertz frequencies. So what you find, in fact, is that for the first generation of terahertz receivers, it looks like it's back to 1901. We're looking at an oscillator as a transmitter and a direct detector, which consists of a diode. In fact, what you do is you look for anything that's nonlinear that still works at a terahertz, and you call that a mixer. So that's what was generation 1. Generation 2 was not different architecturally. It simply increased the amount of power available, and that provided a higher range. So the oscillator powers were increased by 2 orders of magnitude in some, and that enabled greater distances. And now what's happening is folks are finally working on coherent receivers to improve link margins using the same kinds of parts. And the ultimate goal is simply to achieve architectural parity with what we already enjoy in the cell phone world, and that is just a straight-ahead, full-blown, super heterodyne receiver. So many of my students are shocked that the state-of-the-art has not yet even progressed to giving us a super heterodyne architecture. But that's because each of these pieces is incredibly hard to build, and asking for an additional miracle of integrating all of those incredibly hard things is itself incredibly hard squared. So that's the reason we don't have this quite yet, but we're very close to being able to achieve that goal. Now, if we take a look at the transistors that would support this, they are not yet silicon, which is sad to me because I'm a silicon bigot. I'm very, very much biased against anything that's not silicon, not because silicon is the best material, but because silicon does so many things well enough. So if you're talking about an integrated technology, silicon's very hard to beat. But in the case where you just need absolute maximum speed, the physics of silicon are not sufficient, at least at this point. So right now, the state-of-the-art in terahertz semiconductors uses both heterojunction bipolar technology as well as high electron mobility transistors. So both HEMTs and HBTs are currently fighting for supremacy in this terahertz realm. Already, people have demonstrated terahertz Fmax values, not quite terahertz FT, but terahertz Fmax values using indium phosphide as the material of choice for both HBTs and HEMTs. And they achieve this at the 128 nanometer generation. Very, very generous lithographies compared to what we're used to in the silicon world. But because they have such incredibly high mobilities as well as high scattering limited velocities, you're able to get terahertz Fmax values. So in terms of just front-end sensitivity, it looks like these devices will give us acceptable noise and gain in the not-too-distant future. And if you take a look at the ITRS roadmap and all of the calculations that lead to the various values on the roadmap, we can assume that around the 15 to 22 nanometer generation, ordinary CMOS will also achieve Fmax values of about a terahertz. So even though the geometries have to be a lot more aggressive to get there, someone else is paying the bills to move us along there. So eventually CMOS itself will probably be able to support at least receivers at a terahertz frequency. I won't spend a whole lot of time reviewing the structure of a heterojunction bipolar transistor. I just point out a couple of important features. It's a vertical device, it's not a lateral device. So the emitter is here, a very thin base layer is here, and a collector layer is there. And the hetero part is that these are three different 3-5 compound semiconductors. You have a wide band gap emitter, a moderate band gap base region, and a different band gap for the collector. This allows you to trade off things like capacitance against speed, against base resistance, against early voltage or output resistance. So these are very exotic devices. They're all created by atomic layer depositions using things like indium aluminum arsenide, indium aluminum whatever, mixture of indium, aluminum, arsenic, phosphorus, and occasionally things like iron as a dopant, silicon as a dopant. Very, very complicated things, but these are able to work very well. The beauty of this kind of vertical structure is that the critical length is really the thickness of this base region, and that's deposited one atom at a time. So you have exquisite dimensional control over the critical dimension you care about. That's different from what we're used to in CMOS, where you're looking at some lateral dimension. So this enables us to get to these very, very high frequencies without having to do something heroic in lithography. The heroism is in other areas. A HEMT looks more like a MOSFET because this one is a lateral device, and this does suffer from the need for very, very tight lateral dimensional control, but people have achieved that. And as you can see, once again, you have a mixture of sort of the standard materials just arranged differently to provide a MOSFET-like structure as opposed to a bipolar transistor. As I say, both of these have demonstrated terahertz capabilities, and there are differing opinions as to which one of these should become the final winner, but if you ask me which ones to bet, right now I'm betting on the bipolar device. Now, these devices all have given their performance by having process or device designers really earned their pay. They've had to pull off many, many miracles to get us to this point, and more miracles will be required before this becomes a reproducible, high-volume, manufacturable technology. They realize that as you shrink things down to these nanometer scales, things that you didn't have to worry about before now become first-order limiters. Silly things like contact resistance. Right now, it's sort of an annoyance in many circuits. Here, it's the first-order limiter on speed. So we worry about things like contact resistance. We also worry about parasitic capacitances, because you can work it out. You know, what's 100 femtofarads at 1 terahertz? It's a short circuit. So you have to worry about keeping your capacitances down to the absolute minimum that you possibly can. Lateral devices suffer from their own scaling problems. The main thing is just how do you minimize the effective gate length without shorting the device? How do you get the yields to be non-zero and still have tiny, tiny channel lengths? That's a problem that it shares with its CMOS brethren. But nonetheless, it is possible to make enough devices to at least publish at a conference. Whether or not we can put these in high volume production is still an unanswered question. Here's a table which you probably can't see from your seating point. I won't read the table to you. I'll simply point out a couple of highlights that already we can see amplifiers being built with these devices having 1.5 terahertz center frequencies. And that's a roadmap that seems to be based on credible extrapolations of current experimental lab data. So we don't have to invent any new physics, we just simply have to carry out the development program according to prescribed limits. At that point, we'll have Fmaxes that are just a little bit south of 3 terahertz, which is an extraordinary achievement. When I look at these numbers, I have to sort of recalibrate, because I got into the semiconductor, the IC business. When I was in graduate school, there was a transition from 3-micron technology to 2-micron technology. And I thought, wow, 2 microns, that's amazing. How can you do that? And now, that seems like a gigantic skyscraper compared to what we're able to build today. I'll simply point out this is what the devices look like. And this slide also shows us one other thing that's extremely important. The transistor is only part of the story. We have to get signals into the device and out from the device. And at these frequencies, you can't really rely on ordinary wires, at least not for long lengths. So you have to worry about things like launching energy into waveguide cavities. And that's how you propagate this energy out at reasonable loss. If you have any of the energy coupling into the substrate for any reasonable length, all the energy goes away. Think about your microwave oven. It heats food up. This is 500 times the frequency. The heating is going to be large, and anything that contains any lossy material. So you just have to use vacuum as the medium for conveying energy if you want the absolute minimum loss. So that means things like micromachining technology ceases to become an exotic add-on. It becomes almost an absolute necessity in this frequency realm. Here's some plots. There's still controversy about the measurements. As you might imagine, simply proving that you have built a terahertz device is incredibly difficult. And knowing that it's difficult, it's caused some people to be skeptical and say, well, I'm not sure you measured it right. Maybe your fixturing was a little bit off, and maybe you're seeing something that you wanted to see and not necessarily what's actually there. But most people who have looked at the actual data and twiddled their own probes and done their own calibrations find that the curves end up looking like this. This is the maximum stable gain curve. And you find that it does extrapolate out to providing non-zero gain up to 1 terahertz. And so I think the latest read on this field is that, in fact, devices with multiple terahertz Fmaxes have been built, and that gives people some optimism that we can actually manufacture these things going in the future. I won't spend much time on this slide. I'll simply attempt to get through it. But that slide just simply shows that we've got more than one device that supports the idea that these things do work at terahertz frequencies. This reference to the SWIFT program, that's the name of a DARPA program that funded a lot of this work. Okay. If we look forward on this HBT technology, we're looking at being able to achieve, as I say, 2.8 gigahertz Fmaxes in the not too distant future, and that will correspond to sort of a 30 nanometer kind of process, if you want to look at that as being the dimension that you care about most. And at that point, these devices will have breakdown voltages of a couple of volts. We haven't seen those since the 1/4 micron generation in CMOS. And that's another reason why these are attractive. You can run them at higher voltages and thereby get more specific device output power than you could out of a silicon device. It still falls off as 1 over f to the 4th, but that curve is higher. So you can still get some more power out of the device by factors of several, in fact. Now, what if you want to use this for other things? An important idea is that these transistors are useful for many, many applications other than simply functioning at a terahertz. It's the same idea that underpins ordinary transistors. We build transistors with umpteen gigahertz of FT, but we don't always just use them at near FT. We often use them at much lower frequencies where we might be able to trade off some bandwidth for gain. We can use this idea in negative feedback amplifiers to get better linearity and so forth. So think about this terahertz capability as having much broader use than simply working at terahertz frequencies. What has been shown here, what is being shown here is an actual full amplifier device. This one's able to show 18 dB of gain at 340 gigahertz. That's a world's record. And it actually functions. I think a half a dozen of these things have been made, or half a dozen work. More than 6 were made, 6 worked. So that's an impressive achievement. And just simply, again, doing the measurements, how do you calibrate a network analyzer at these frequencies? That involves heroism of its own. It's very important when you work at these frequencies not to forget about interconnect. This is a tragic mistake that a lot of newcomers to the field make, and they learn very quickly. They can't ignore it. You need to take some of your best people and have them work on just the interconnect question. You end up doing curves like this. At nearly a terahertz frequency, the skin depth in metal is something like 50 nanometers. And that means that whatever metals you lay down have to have surface roughness that's small compared to 50 nanometers. That's not trivially achieved. You can achieve it, it's not trivial. You have to pay attention to it. You have to make that a specific goal. If it has surface roughness that's comparable to or greater than the skin depth, you find that the total path that the waves have to traverse is lengthened, and so the equivalent skin loss goes up by large factors. Textbooks say a factor of 2, including mine. Turns out those textbooks are wrong. Measurements show that the surface roughness can have a much greater effect for reasons that Jim Raudio of Sonnet Software has recently explained. So you end up having to do these kinds of curves to make sure that you choose both the dielectric thickness and the metal thicknesses appropriately to minimize the total loss. And right now the tools that we have to make these calculations are kind of not very well developed. You can use, as I say, the terahertz performance to give you incredibly good amplifiers. You can build op-amps, for example, that work at 100 gigahertz thanks to terahertz transistors. Imagine having an op-amp with a terahertz gain bandwidth product. Wouldn't that be neat? That would give you amplifiers with incredibly good linearity. Right now we don't think of negative feedback as being useful at high frequencies simply because negative feedback requires large excess capacity, large excess capability in bandwidth terms. Well, here you have it. And so all of a sudden you can do things that you thought were only low frequency ideas. You can apply them in the millimeter frequency band. And that itself can be transformative for things like A to D converter front ends, A to D converters themselves, D to A converters, as well as LNAs and other standard blocks. I won't spend a lot of time on this, but just point out that you can expect large IP3 improvements. You can build DACs that would clock in excess of 100 gigahertz. I think you can probably figure out some exciting uses for blocks that have that kind of performance. Now, if we go back to the question of output power, what you find if you look at the plots more closely is an interesting divergence between what vacuum tubes can do and transistors can do. And you might be shaking your head going, vacuum tubes? Why is this guy talking about vacuum tubes? I kind of remember my grandfather playing with vacuum tubes. Why are we looking at terahertz and vacuum tubes in the same sentence? Well, the reason is because of the differing physics. And we're going to take a little detour to spend some time looking at the physics to explain why vacuum tubes deserve much more attention from a young crowd. So the idea here is first to start off by asking the question, well, why didn't vacuum tubes take over the Earth? Well, part of it is that they're a complicated 3D structure, and once we had the planar transistor, we didn't need them. But if we're looking at very, very high frequencies, if it's true that vacuum tubes have some advantage, how come we're still playing around with semiconductors at terahertz frequencies? Well, there are lots of reasons. One is, as you go to higher frequencies, you have to shrink things to the point where ordinary manufacturing technology just can't give you those tiny structures. Another one is that as you shrink things, it turns out to be difficult for standard electromagnetic field reasons to couple energy efficiently out of the device and into the device. And it turns out there's another important parameter which I won't spend much time on, but we have to worry about electrons having divergent energies. If they have non-uniform energies, then some electrons end up getting ahead of some other ones, and that serves to behave very much like scattering within a semiconductor. It has the same bad effects and causes the gain to degrade and the noise to increase. So that's why people kind of gave up vacuum tubes. Now here's what a vacuum tube looks like for those of you who don't know what that is. You have a source of electrons. In the classical case, you just heat up a piece of metal. Electrons are freed from the surface. You have an anode that's positively charged. Electrons accelerate over there. Then you have these porous grid-like structures called grids that you apply voltages to that you can use to modulate the amount of current. So that's how you get a transistor out of this thing. This is not a solution by itself. This is just by way of getting to the solution. The solution, or one of the first solutions, was invented at Stanford in 1937. It's this thing called a klystron, and the idea is very clever. How do you convert DC into microwave directly? And this is how they did it. You take a filament, just like a standard vacuum tube or a light bulb, and you shoot it through this resonator. This resonator is a cross-section here of something that looks like a kind of a mush dumbbell. You have a closed structure that consists of what may be regarded as a single-turn inductor in parallel with a capacitor. So this forms a resonant circuit. But this capacitor has holes in it. So that as the electron passes through it, it experiences the electric field across those capacitor plates. Depending on the capacitor's voltage, the electrons are either slightly accelerated or slightly decelerated. That will become important later on. At some point downstream of these both accelerated and decelerated electrons, the slow ones will have been caught up by the fast ones, and you'll end up with a non-uniform electron density, and that gives you something that has an AC component, and you can pick off a harmonic of that with another filter, another resonator, and that energy comes out. So DC went in, RF came out. Here's a picture of how a klystron works. Here we have a uniform emission of electrons, so this represents a steady state current. As it passes through these capacitive plates, it either speeds up or slows down, so we end up with something that's a non-uniform density of electrons. If we take a look at the x-axis here and simply plot the current as a function of time at those various locations, you see we start with a uniform current, and as we move to different locations, we can end up with something that has extremely high harmonic energy, and that's what you pick out with this second resonator. It was a brilliant structure because it showed that you could use these cooperative behaviors of electrons in ways that you can't do in a semiconductor, because semiconductors scatter the electrons. You can use this ballistic transport to give you a device behavior that is extremely useful. And that's how, before World War II, we were able to make gigahertz structures out of things whose dimensions were denominated in millimeters. Pretty impressive thing. Now, if you tried to take this and simply scale it up in frequency, people have tried to do this, they have failed spectacularly. This does not scale gracefully at all. And there are lots of problems. One is simply that these grids occupy too much of the cross-sectional area, so the electrons bump into them and don't make it to the final destination, so you just have bad efficiency. Another problem is that if we try to scale this device in an effort to get other than kilowatts, we end up with a very high impedance, and that does not couple efficiently to the outside world. The energy just rattles around inside and eventually dissipates, as opposed to getting outside the device. So these folks at JPL, very smart folks, if they couldn't do it, you can assume it can't be done. So they failed, and for reasons that we think we understand. So that's not the way to get there. There are ways to get there by being a little bit more clever about how we pull energy out of the beam. We can do it in steps. So we can use multiple cavities all structured together in an effort to make that transition from high impedance to low impedance more graceful. So here's a single cavity, here's multiple cavities. You can extend this to as many cavities as you think you can build, and you can end up with a very, very broadband, exceptionally high power device at terahertz frequencies. Manufacturing difficulties are extremely high, but people have been pursuing this and have demonstrated sort of 50 to 100 watts at a couple hundred gigahertz using vacuum tube structures. They've made sort of one of these, but it shows the basic principles are sound. Here's another approach. Rather than sort of taking the electron beam as it whizzes by and try to extract energy out of it, why don't we give ourselves a luxury of taking the energy out of it in multiple steps, kind of like taking the extended interaction device, but folding it on itself. The idea is this. If we can take an electron and simply cause it to undergo if we can cause it to undergo multiple oscillations like this, it doesn't have to hit this plate until finally all of its energy has been given up to the outside world. So the idea is to give us a chance to extract energy out of it multiple times. You can do this by setting up what's called a quadrupole field. We can set up a quadratic potential well that feels just like a pendulum in the Earth's gravitational field. So we set it swinging, it swings back and forth, and as we pull energy out of it, the amplitude just goes down. But we still get all the energy out of it when all is said and done. So the idea is we send some electrons flying from left to right, but as they do so, they head back to the left, and they go back to the right. They just go back and forth, and we take the energy out laterally, coupled through some dielectric waveguides to the outside world. It might look something like this. This is what we're trying to build at Stanford. It's very hard because I'm not a micromachining guy, and my students are learning how to become micromachining people. And they're concluding from this that they never want to be a micromachining person in real life. But we have managed to build a few things like the electron sources. And here's what they look like when you finally master the art of high aspect ratio etches on silicon carbide. And these devices are standard emitters just like your grandfather used to use. You just put enough voltage across this thing to heat it up, and it glows, and electrons come out. And you can use that to accelerate electrons into the cavity. Of course, if you want to be a little bit more advanced, you can consider field emission as opposed to thermionic emission. And so people have demonstrated very, very sharp tips using things like diamond. And these emit extremely well. These were originally developed in an effort to compete with plasma and other kinds of flat panel displays. The uniformity was just never good enough to make that practical. But for us, we don't care about uniformity. We just care about enough emission to get the job done. So we can take all the work that people did in the flat panel era to make our work better. So one of these days we'll get together with groups that have done these kinds of emitters and combine them with our structures. And I'll just end up by showing you that this is a technology that probably doesn't have much of a future simply because it's not easily scaled. It doesn't easily leverage the aggregate investment in semiconductors. This is a full 3D structure if you want to build vacuum tubes that look like this. This is just I think, a show-off achievement that if you pay enough money to smart people, they will build almost anything. The future, I think, lies in coming up with a semiconductor concept that enables you to achieve the same sort of low scattering. In other words, a large coherence length of carriers in a semiconductor material so that we can use the same tricks that the vacuum tube people exploited 60 years ago, but do them in a full planar or quasi-planar structure so that we can use all of the art that we've spent so much money to develop in the semiconductor world to get terahertz out of it. But at least we'll start with vacuum tubes and then move on to semiconductors, kind of reversing the flow of history in that case. So in closing, I just want to point out the terahertz gap, this last band of frequencies, demands exploitation. There are compelling applications, which means that we will fill that gap. Semiconductors will do well at the lower power end. Eventually, vacuum tubes will take over the high frequency end. And bridging the terahertz gap will give us things like at least line of sight, terabit per second, on demand, extreme wideband communications, as well as these medical imaging and security applications we talked about earlier. Thank you very much.